Okay, here is the video on optimization, and here's what I highlighted that I thought was important. Optimization is one of the most common applications in calculus. We often hear terms like least time, greatest profit, shortest distance, maximum volume, minimum waste. So in order to optimize problems of this sort, we first need to find the quantity that needs to be minimized or maximized. Be sure to assign variables and write a function that represents the minimum or maximum needed. Then use the techniques we've learned in this chapter. What we're going to call our primary equation is an equation that gives a formula to the quantity to be optimized. And we'll also have secondary equations, and those are the ones that provide information needed to complete the primary equation. So let's get started. Example 1 says, find two positive numbers such that the sum of the first and twice the second is 64, and whose product is a maximum. So we're going to start with x being the first number, y being the second number. We want the product to be a maximum, so we're going to call that our primary equation. And that is going to be x and y. Our secondary equation will be the sum of the first plus twice the second being equal to 64. And on our primary equation, we're looking for a maximum. So we're going to take our secondary equation, we're going to solve for y. Subtract the x, divide by 2. We're going to take that and substitute it into our primary equation. So f of x equals xy. Well, that'll be x. Y is the 64 minus x divided by 2. If we distribute that in, that's 64x minus x squared, all of it divided by 2. And we can simplify it to be 32x minus 1/2 x squared. And then we're going to take the derivative of this function. So f prime will be 32 minus x. We're going to set it equal to 0. So 32 minus x equal to 0, and x will equal to 32. From here, we're going to use our first derivative test to ensure that this is going to fall into the requirement of it providing a maximum. So we're going to go off to the side, create a sign chart. We got 32. Numbers below 32 will increase. Numbers after 32 will decrease. So in fact, this will be a maximum. So with x being 32, to find our y value, we know that y was equal to 64 minus x divided by 2. Replace x with 32. So 64 minus 32 divided by 2. and that gives us 16. So our two answers are 16 and 32. Our next example says a farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? So before we start this one, let's draw it out. So here's the river. Our primary equation will be the perimeter. Excuse me. X plus 2y. And our secondary equation will be the area, which will just be xy. And we will use our secondary equation and get y by itself. We know that the area needs to be 180,000. Once again, we'll solve for y. Now we're going to take our primary equation, substituting our y value, to find the common denominator. We won't need to. I'm going to make it more complicated. So this is the function we're going to use. From here, we're going to take the derivative of each part. So it'll be 1 minus 365 inverse squared. We're going to set it equal to 0. X squared equaling 36,000. Plus or minus 600. We know that dimensions can't be negative, so we're going to go with the positive one. And we're going to create our sign chart. We have 600, values below it are negative, values above it are positive. So this indeed is a minimum. So now our x is 600, y was 180,000 divided by x. So this will be 180,000 divided by 600, which will give us 300. So our pasture will be 300 meters by 600 meters. This next example is a typical question that you will see on an AP exam. And this next question is telling you, an open box is being constructed from a piece of sheet metal 18 inches by 30 inches by cutting out squares of equal size from the corners and bending up the sides. What size squares should be cut to make a box of maximum volume, and what is that volume? So first, let's draw this out. We know that it's 18 by 30, but we're going to be cutting out some squares. So we don't know what these are yet, but you know that a square has the same length on all sides, so we're going to call it x. Well, then that's going to change the dimension of our box. This will now be 18 minus 2x, because we're going to remove an x from here and an x from here. And this will be now 30 minus 2x, because we will be removing this from here and this from here. So now, our very first step to find volume of a rectangular solid is just length times width times height. So our volume here will be our length, which is 30 minus 2x, our width, which is 18 minus 2x, times our height, which we're going to call x. If we FOIL this out and distribute the x, we're going to get a volume of 4x cubed minus 96x squared plus 540x. Our next step will be to take the derivative, which will be 12x squared minus 192x plus 540. We will take this, we can actually factor out a 12 from all the terms. Set it equal to 0. And then we can do a completing the square with what's left over. So it'll be x squared minus 16x plus something, 45 on the outside. Whatever we add on the inside, we're going to subtract on the outside, and that'll be equal to 0. This something is actually half of b squared. So half of 16 is 8. 8 squared is 64, so we're going to add 64 on the inside. We're going to subtract 64 on the outside. This now becomes a perfect trinomial, which means if we were to do tic-tac-toe on this, we end up with x minus 8 squared. Simplify this, that becomes negative 19 equal to 0. So x minus 8 squared equals 19. And x is actually going to equal to 8 plus or minus the square root of 19. If we check both terms, we are looking for the minimum amount of x that will give us the maximum volume, so we'll take the negative one. You can check both, but you'll take the smaller of the two. So 3.641. Now, if we take this and substitute it into our volume formula, we actually get a volume of 886.553. That's actually the maximum value we can get with the most minimum value of x. So, to summarize, we're going to cut squares approximately 3.641 inches for a max volume of approximately 886.553 inches cubed. The next equation is asking us, what is the largest possible area for a right triangle with a hypotenuse of 5 inches? Well, we're going to call x the length of one leg in inches, and y the length of the other leg in inches. Our primary equation in this problem will be the area, since that's what we're trying to maximize. Area of a triangle is 1/2 length, or base times height. And our secondary equation, since it's a right triangle, x squared plus y squared, and we're looking for a hypotenuse of 5 inches, so that's 5 squared is 25. We're going to solve for y. Y will be equal to the square root of 25 minus x squared. From here, we're going to go on to our primary equation. Substitute in our y value. And now find the derivative. So a prime, this is a product rule together with a chain rule. So it'll be the first times derivative of the second plus the second times derivative of the first. And then we're going to simplify this. And we'll actually end up with a negative x squared on the top for the first part over 2 square root of 25 minus x squared plus the second portion being 25 minus x squared, all of it divided by 2. Now we're going to get a common denominator between the two, which will be, multiply this one by 25 minus x squared. And once we combine our like terms, we'll end up with negative 2x squared plus 25, all of it divided by 2, square root of 25 minus x squared. And again, we're going to set this equal to 0. If we write 0 as a fraction over 1, we cross multiply. This will be negative 2x squared plus 25 will equal to 0. We're going to try to get x by itself. So take the square root of both sides. Square root of 25 is 5, square root of 2 is square root of 2, which is what we'll leave it at. So now we're looking for the largest possible area, so we're going to take the positive of the two answers we would get. Now we know that x equals 5 over the square root of 2. If we solve for y, we add 25 minus 5 over square root of 2 squared. And that'll actually also give us 5 over square root of 2. To find our area, it'll be 1/2 x times y, which will then give us the largest possible area of 25 over 4 inches squared. And our last question is asking us, which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So if we draw this out, we know that it's a concave down parabola with a y-intercept at 4. But we want to see which one's closest to 0, 2. I'll call this one x2, y2, x3, y3. Our function is 4 minus x squared, and our point is 0, 2. So what we're going to do first is we're going to use the distance formula. which is x or y2 minus y1 over x2 minus x1 squared plus y2 minus y1 squared. So we're going to take x minus 0, because this is actually our x1 or y1, minus 0 squared plus y2, which will be our equation, so 4 minus x squared minus 2, and the whole thing squared. From here we can simplify it to be x squared plus 2 minus x squared squared, all of it still inside the square root. If we FOIL that second parentheses out, we end up with x squared plus 4 minus 4x squared plus x to the 4th combining like terms, we'll end up with x to the 4th minus 3x squared plus 4. And from here, even though it's all within a square root, because it's within a square root, we don't actually need to use the square root anymore to find the smallest critical values. So we're only going to focus on the inside. And we'll take the inside, find the derivative, set it equal to 0, create our sign chart. For these three values. So 0, negative, cube root of 3 halves, positive 3 halves. Anything below that into the first derivative will be a negative, then a positive, then a negative, and then a positive. So we know that from negative to positive, this will be minimum. Positive to negative is a maximum. Negative to a positive is a minimum. We're looking for the closest, so we're looking for the minimum values being negative square root of 3 halves and positive square root of 3 halves. So we now know that x is equal to both plus and minus square root of 3 halves. To look for y, it's 4 minus square root of 3 halves squared. So our y value will actually be 5 halves. And to summarize, when x is the plus or minus square root of 3 halves, the points closest to 0, 2 on the curve